There is something called electroscope, which is made of a knob, which is the circle, made of stem, and made of leaves. Okay, so let's just say here we have a positive charge and a negative charge, which means neutral, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, and so on. Here, the number of the positive charges is the same as the number of the negative charges. We call this object neutral object, which means not charged. Okay. Now, if I were to bring a negatively charged rod very close to it, what I will do is that I'll be pulling all the positive charges close to the negative rod and pushing all the negative ones away from it. So, I'll be pushing the negative one away, down. I'll pull the positive ones up. Okay, pull the positive one up. All right. Pull the plus ones closer to the top, essentially. And
the negative one's down.
Negative ones will go down. Exactly. So these guys will go down. This one is also going to go down. You see how all the positive charge is now centered toward the top and negative one centered toward the bottom. What's going to happen is you have too much negative on the bottom, negative repelling negative. This leaf will then extend away, right? It will get pushed away. So now my new leaves will be placed here and there. So I'm going to have 1, 2, 3, 4, 1, 2, 3, 4. Repulsion happens. So the leaves push away from each other due to repulsion.
They are negative, and negative and negative repel each other.
Exactly.
Positive and positive repel each other.
Exactly. So what I just witnessed happening here is something called charge redistribution. The negatively charged rod did not touch the electroscope, but it simply resulted in the shifting of the charges for the plus to move closer and the negative to move farther away. It's called charge redistribution or charge polarization. Okay? Now, has the amount of charge on the electroscope changed? No.
No, it's just was repelled.
Mhm.
Was repelled.
Electroscope is still neutral. Okay? Okay, so let's just say that we have an electroscope, a knob with a stem and with the leaves.
Yes.
Okay. Let's say that we have a negatively charged rod very close to it. What's going to happen?
Positives go up, negatives go down.
Exactly. Positives go up and the negatives will go down. Okay. Now what happens is you could possibly touch this electroscope with your hand.
Yeah.
Or you could attach the electroscope with a wire to the ground. Okay. If you touch it with your hand or if you touch it with a wire to the ground, this is called grounding effect or just grounding. Okay? What grounding does is that it will give a path for these electrons that are sitting in the bottom to flow down the path. So now all the electrons here will flow down to here. Okay? Now, while keeping the rod close by, I want you now to cut the path. So cut the wire.
Yeah.
And now the electroscope will only contain positive charges because all the negative left to the ground.
Yes.
Good? So now the electroscope is positive.
Alhamdulillah, something that makes sense.
Yeah. So the negative left, the positive stayed, right? The rod stayed negative, and the electroscope now became positive. So we just changed the charge of the electroscope without touching it by the rod. Okay? Good. Very, very good. Now, let's see if we have a neutral sphere. Neutral means it has an equal number of positive charges and negative charges. Let's say we have 3 and 3. Okay. Right now, if I take this sphere and I connect it to the ground by a wire,
Yeah.
this is the wire. What's going to happen is, now if I bring a negatively charged rod close to the sphere,
Negatives go up, positives go to the ground.
why?
Because of the wire. Positives go up and negatives go to
The negatives will actually now travel
Yeah.
all the way to the ground
to
as
the
well.
ground. Yeah, because
Okay? So all the negatives have left the sphere, and now you can cut the wire,
Yes.
and now your sphere
Now,
is positively charged.
Yeah.
Good?
Yeah.
But you see, you must always cut the wire while the rod is close by.
Like how? What?
So we cut the wire and we kept the rod
Close.
close. We did not remove the rod. We kept it close. Okay? So this will ensure that the sphere gets
And
charged.
instead, if we remove the rod, positive and negative will go to the ground.
Right now?
Yeah, if we just remove the rod,
No, nothing will happen.
nothing will happen.
No, you must always cut the wire, then remove the rod.
Yeah.
You see what's happening here? If the rod is negative,
Positive.
the sphere is positive.
Yeah, and if it's positive, it's negative. The sphere is negative.
Whatever the rod is, the sphere is going to have
Opposite.
the exact opposite charge. Good. Now, if I have a sphere whose charge is +5, and I have a different sphere with the same exact size whose charge is -2, and now I bring them to be physically touching each other.
Yes.
Let me just make this sphere the same exact size so the people who see the video don't get confused, right? But let me make the charge now negative. And now let's make those two spheres physically touch each other. What's going to happen? The charges will add up. So now you're going to have +5 -2. So these will be going away. You get how much?
3.
3. Okay?
Yes.
Now, let me just use an even number because 3 is an odd number. We can't have half a charge. Let's do +6 -2. That means I will get 4. Now, since the spheres are the same exact size as each other, they will divide this 4 by 2 exactly. So we're going to have a +2 here
And a +2 there.
and a +2 in the other one. Okay? That's only if the spheres were the same size, they divide the charge equally. If they were different size, the bigger sphere takes up more charge. For instance, let's say one sphere was very big, one was very small. Maybe the big sphere will get 3, the small one is going to get 1. Big sphere gets what? gets
Sure.
more charge.
And like, how do we know exactly how much does each get? Like, if it's 8,
Uh-huh.
the big one will take 6 and the small one will take 2.
We don't know how much, but we just know that more than half
It will
will
take
go.
more. So I need to know generally it will take more.
Exactly. Good?
Yeah.
All right. Okay. Now, let's talk about a metal. Is a metal conductor or insulator?
Conductor.
Thank you. A conductor has a quality of having zero charge in the inside. All the charge has to go on the outside. And if you have zero charge on the inside, you will have zero electric field on the inside. But non-zero electric potential. So zero electric field, but non-zero electric potential. Good?
Yep.
So all the charges have to go on the outside
Yes.
of that sphere. Okay, now, there's an equation that you have to know for something called the electric field. Electric field is equal to KQ over R squared. R is the distance. So what's the relationship between the E and the R? Inverse or direct?
It's inverse.
Inverse. So E is going to be inverse with R squared. That means as the R goes up, the electric field will go down. Okay. Very good. Now, we said that inside we're going to have a zero electric field, but not zero electric potential, also called voltage. Let's explain that. So, let's just say the center of the sphere is 3 meters away from the outside of the sphere. And did you know that the voltage at any point here is the same as long as the voltage is inside the sphere? For example, at 1 meter from the sphere center, maybe the voltage is 5. At 2 meters, the voltage is still 5. At 3 meters, the voltage is still 5. So the voltage within the radius will not be changing. So why is that? Because the voltage has an equation. V is equal to K Q over R. And inside the sphere, the least possible R is the radius, which is 3 meters. For example, if they say find the voltage at 1 meter away from the center, you will say V is equal to KQ over 3.
Yeah, and the old formula was K equal VQ over 3.
Look, what I'm saying is, at any point within the radius, you always have to put the radius in the bottom. So if they want the voltage at 1 meter, you still put the radius. They want the voltage at 2 meters, you still put the radius. They want the voltage at 3 meters, you still put the same radius. You only put a different number when you are away outside the sphere. For example, if they say find the voltage at 5 meter, you are already outside the radius, you just put that 5. What this tells us is the voltage, imagine if I had points, point A, point B, and point C. Will they have the same voltage as each other?
Yes.
Yes, because they are all within the same, all inside the sphere. So the voltage of A is equal to the voltage of B is equal to the voltage of C. So please keep that in mind.
Yeah. So far, I haven't seen it.
I'm glad. Okay. Imagine now if I have an uncharged object, meaning I have an equal number of plus and minus. Okay, if I bring next to it a negatively charged rod, will the uncharged object feel attraction from the rod or repulsion?
It will be, well, the positives will be attracted, but the negatives will be repulsed.
So, will this uncharged object move closer to the rod or move farther from the rod?
Well,
Move closer.
closer.
And like you said, you're going to have all the positives on the right, all the negatives on the left. Let's now change the scenario. What if I made the rod positive?
It will be the opposite.
It will still move closer,
Yes.
but now
Negative
we're going to have the negatives here.
And the positives.
Uh-huh. But in both cases, uncharged object gets attracted to a charged one. Okay. Now, so far we've been talking about a conductor. This was a metal, which means a conductor. How about a non-metal, which means an insulator?
Yes.
What happens there? Can the charges move in a non-metal? No, they cannot. All they could do is, let's say here we are representing 6 atoms. The atoms cannot move, but the dipoles could. So if the atom has a plus and a minus, plus will be facing this way, to the right side, and the minus will be facing to the left. Do you see what's happening here?
Yeah.
The charges don't move, but the orientation of charge within the single atom will change orientation.
And also a non-metal will not be attracted, will not move closer to the rod, right?
It could.
Good?
Yeah. Just like there is an experiment where you cut a piece of paper, like small pieces, and you rub a ruler against your head, against your hair, and you bring it close to them, they're going to start to jump to it. That's insulator attracting another insulator. So attraction could happen. Okay, and by the way, if you recall, for a conductor, all the charges went on the outside.
Yeah.
For the insulator, they're going to be found outside and also inside.
Both sides.
Yeah. So for the insulator, you're going to have some charges on the outside and some will be on the inside. Meaning electric field in the inside is not equal to 0 anymore. Okay. If I take 2 charges, one positive and one negative, the electric field will always go from the positive charge to the negative charge. In circles. Like this. Cool?
Yeah.
Very good. Now, let me just draw an object with a weird shape. Do you see a sharp end?
Yes.
Good. Just do it again. On the sharp end, the charges will accumulate to a higher degree. So let's say this object here is positively charged. You're going to have more of the positive charge on the end than on the sides. All right, electric field always leaves a positive charge. Like this. You get the idea, right?
Yeah.
Okay. So let's just say that here I want to represent the drawing of a positive 12 charge with a negative 8 charge that are not physically touching each other. Which one do you think will have more electric field? The plus 12 or the minus 8?
Electric field?
Mm-hmm.
Negative?
No. You look at the number only, not the sign. So that means if I draw lines between them, if I draw 1, 2, 3, and 4, coming out of the positive charge, right? I mean, yeah, the negative charge. And let's say from this side I have 1, 2, and 3. Do you know what's happening here? So I have 1 and a 2 and a 3. So any arrow going to the negative charge has to be coming from the positive charge.
Yeah.
Now what if I have two negative charges sitting right next to each other?
They won't attract.
They will not. Their fields will be repelling each other like this.
Yeah.
It's like having a field has to be going inside a negative charge. Like this.
They'll push each other up.
They push each other away. Exactly. They push each other away. Okay? Excellent. Now, if I have a negative charge, here I have a positive charge. Okay. And are they going to be attracting each other?
Yes.
With the field going from the positive to the
Negative.
negative. That's cool. Now, there is something called equipotential surface, which basically means concentric circles formed around the charge. So like if I take a positive charge here, I can draw around it 1, 2, 3. That means we have 3 equipotential surfaces. If I take a negative charge, 1, 2, 3. Again, 3 equipotential surfaces. But when they're placed next to each other, when I draw these circles, it's going to be closer between and farther on the side facing nothing. So closer between and farther on the side facing nothing. Closer between and bigger on the side facing nothing.
Attraction is happening on that side.
Exactly. Good. Now, there is something called voltage. Voltage is equal to K, Q over R. Okay?
Yeah.
Now, these charges, one is positive and one is negative, correct?
Yes.
Okay. At the center, between them, how much will the voltage be?
Center.
0. Because they have the same exact charge. So at the distance, in the midpoint between them, you're going to have a 0 voltage. A 0 voltage has to be represented by a straight line.
And what if they are not like the equal charge? They are not equal.
It's going to be somewhere closer to the
Bigger charge.
bigger charge. No, to the smaller charge. Okay. Now, so this straight line here is called an isoline. An isoline of a 0 voltage.
Yeah.
All right. Very good. Now, let's talk about having a positive plate facing a negative one. The field is going to go from where to where? From the positive to the
Negative.
negative. So red line is going to be the electric field.
Yep.
If I have a positive charge here, where is it going to head toward?
To the negative side.
How about a negative charge?
To the positive side.
Exactly. Now, so what's happening here is that the positive charge will move along the electric field. While the negative charge moves opposite of the electric field. So because the positive charge moves along the electric field, that means the electric force and the electric field are in the same direction. But if it's moving the same direction, but if they move opposite to each other, that means electric field and electric force opposite. Just know that in a positive charge, electric field and force move in the same direction.
Negative
For
is
negative,
opposite.
exactly. By the way, voltage is going to be the highest at the positive end. Let's say, for example, this is 10 volt. At the positive end, it's going to become 8, 6, let's say it's going to become 6, 2, and then 0. The biggest voltage at the positive end, lowest voltage at the negative end. Okay. Now, if I draw the equipotential surfaces, which are circles around a positive charge, they're not going to have the same distance between them.
Yeah.
For example, let's say from here to here, there's distance of 1. But then from here to here, distance might become 2. Maybe from here to there, distance becomes half. What I'm saying is the distance between the consecutive circles is not uniform. Your book made a mistake by making them uniform. That's a big mistake.
It's random.
It's random, exactly. Also, speaking of electric field, you see how the voltage starts high at the positive and becomes low at the negative?
Yeah, because the
Elec-
energy is flowing from the positive to the negative. Right?
No, but this would not apply for electric field. Electric field is going to be uniform, which means constant throughout. Constant. Very good. So, if I take this capacitor plate again, while the electric field lines head down, the ISO lines, which is the voltage lines, are going to be perpendicular to them. So this blue is called an ISO line, which means voltage line.
Which is always 0 because it's in the middle.
No. Oh, no, it's going to be not 0 because these are plates, not charges.
Yeah.
And the red one is going to be the field. They will always be perpendicular to what? To each other. Now, let's take those two plates again. And now, let's take a positive charge and make it go through the fields. Will it stay in a straight motion or is it going to curve?
It's going to curve, right?
Toward where? The negative or positive?
The positive and then to negative, right?
No, it's going to curve toward the negative.
Yeah, it's turning.
Right?
Yeah.
In fact, it's going to be undergoing something called parabolic motion. What are the properties of parabolic motion? It has two components of velocity, Vx and Vy. The Vx will remain constant, while the Vy is going to increase over time. Okay? It's going to increase over time.
Yeah.
Very good. Okay. Now, let's take a positive charge and negative charge. In the point midway between them, the electric field will become maximum, but the voltage will be 0. Why is the electric field maximum? Because field always leaves the positive charge, always goes to the negative charge. Exactly. And if the electric field is maximum, the electric force is going to be also maximum. Look, I want you to compare two things. Let's compare two things. Let's compare electric field to voltage. Which one is scalar? Which one is vector?
Which one's scalar?
What does scalar mean?
Yeah.
No direction.
No direction.
Scalar, vector. Electric field has an absolute value, which means always positive. But scalar has no absolute value, can be positive or it can be negative. When adding two electric fields, you must look at the direction. When adding two voltages, you don't care about direction. Okay? For the electric field, sometimes you have to use the Pythagorean theorem. For example, if one field goes this way and one goes this way, you must connect them by the Pythagorean theorem. This would never happen for a voltage. So voltage is going to be much easier to work with. Much easier. Okay? Let's look at this AP question here. We have two non-conducting spheres, which means non-metal, are fixed in place, QA and a QB. Okay, one is plus 3Q and a distance of 6Q from the origin, point P, and one is at charge of -4, has charge of -4 and a distance of 4D. Okay? Mm-hmm. Now, I want you to work on find, 1 second. I want us to find the electric potential at point P.
Pythagorean theorem, right?
No, electric potential only requires addition. No direction is required.
So 3 plus -4, we're gonna get -4.
No. Electric potential has an equation. K QA over R plus K QB over R. You know what K is, right?
Yes.
Okay. So 9 times 10 to the power of 9. And QA is going to be 3. And how far is QA from the origin?
QA?
Mm-hmm.
It's 6.
6D. 3Q and 6. Wait, am I doing QA? Yeah, I'm doing QA. Okay, so 6D. And KQB over R. So this is the K. QB is -4Q. And how far is QB from the P?
4.
4D. Now you cannot stop here. We must actually do some math. Okay. And you know, I want you, it's okay if you leave K as K. So you know how I replace K with this number? That's okay, just leave it as K. They accept that in the exam. Because for these questions, they're going to say derive an equation, derive an expression or an equation. So that means you just leave your answer as letters. But of course, we're not done yet. So what's K times -4Q? -4KQ. What's K times 3Q? 3KQ. Now what I want you to do is, I want you to take these and make them the same denominator. 6 and 4 meet up at what number?
12.
So, to make 16 into a 12D, you must multiply it by
Both
2,
sides by 2.
by 2.
Both sides by 2.
Uh-huh. So we're going to have 6KQ minus 12KQ. We're going to have -6KQ
over 12D.
over 12D.
And that's our answer?
Not yet. -KQ over 2D. That's how you find the voltage at point P. Now find the electric field at point P. The equation is going to be K absolute value Q over R squared. So look, for QA, we're going to say K absolute value QA over 6D
Squared.
squared. Okay, so K times 3Q over 36D squared. Let's simplify, it becomes KQ
Over 12.
D squared. How about a QB? K QB
It's gonna be 4 because absolute value.
4D.
It's gonna be squared 16.
So K times 4Q over 16D
Which equals
squared
1 KQ over 4.
over 4
D squared.
D squared. Now, how do we add them to each other?
How do you do Pythagorean theorem?
Do the Pythagorean, right?
Yeah.
Okay. So, why the Pythagorean? Because the field goes out of QA and goes into QB.
It's
They're what? Perpendicular to each other. Same as do the Pythagorean theorem of KQ over 12D squared plus KQ 4D squared. So we're going to have K squared Q squared 144 D to the power of 4 plus K squared Q squared 16 D to the power of 4. Now make them the same denominator.
Same denominator?
So 144 and 16 meet at what point? At what number, I mean? You don't know it. Okay, well,
I think
they meet at 144.
144, 16 multiplied by 9.
16 times 9 times 9.
Yeah.
So we're going to have K squared Q squared plus 9 K squared Q squared. And here we're going to have D to the power of 4. So we're going to have 10 K squared Q squared over 144 D to the power of 4. So we're going to end up with square rooting everything. So root of 10 KQ over 12D squared.
Instead, just over there, we turned 16 over to 144.
Yes.
And then did we add? No, I mean, they stayed the same.
Yeah.
Denominator stayed the same.
Yes.
But the numerator
Changed.
changed, yeah.
Yeah.
Okay, yeah. That's...
Good. That's how they're different from each other. Okay, now let's talk about something new called electrical potential energy. So if you want to push two oppositely charged particles away from each other, you have to exert positive work. Because look, they already want to go toward each other, correct?
Yeah.
So that means if you want to pull them away from each other, you have to exert positive work. You have to exert positive work. And exerting positive work will increase the potential energy of the system. So this increases the potential energy of the system. Now, what if you have two oppositely negative charges, right? And you want to push them toward each other. They're already pushed toward each other, right? So that's called negative work. You have to exert negative work, and this will decrease the potential energy of the system.
But
So
what is positive work like exactly?
Positive work means you have to exert a work on your end. Yeah. So look, if they were already moving toward each other, and you just make them move toward each other more, that's called negative work.
Yeah.
But if they are moving toward each other and now you make them move away from each other, that's called positive work. Very good. Let's now do an example in the book. So that'll be example 2 of this chapter, which in Princeton Review is chapter 4. So we're going to have 4 equal positive point charges situated at the vertices of a square. So plus 1, let's say plus, 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 and plus. This is the center of the square. Find the net electric force on a negative point charge placed at the center of the square. So, this positive charge will be pulling on that negative. This positive charge pulls on the negative. This positive charge pulls on the negative, and this one pulls on the negative. Since this negative charge is the same exact distance from all the positive charges, and since all the positive charges have the same magnitude as each other,
it will stay in its place.
Exactly. So the F net will be 0. And the negative charge will not move. Good?
So if you want more, I can
No. Love the amount. Okay. Now let's move on to example 3. Things are about to change. What example 3 says, assume the 2 positive charges on the bottom side of the square in the previous example were removed. So now we just have plus here, and plus here, and minus here. What's going to be the net electric force on the negative charge? Okay, so look.
Still, the negative charge would go in the middle and like it wouldn't go to any of them.
You're right. We should actually calculate how much that is. So the square, that's our square, correct?
Yes.
Okay, how long is the side of this square? 4. Right?
Yeah.
But 4 to the center only. It's going to be 2, right? Does that part make sense or no?
Yeah, it does.
Okay. And it's also going to be 2. And that is going to be 2. And that's going to be 2. Now, if I have a triangle with 2 in here, with 2 in here and 2 in here, how much is this part? How much is the hypotenuse? I must use the Pythagorean theorem. So it's going to tell me 2 squared plus 2 squared, which means the root of 8 in centimeters. So in meters, that'll be the root of 8 divided by 100, correct? So distance between the negative charge and each positive charge is the root of 8 over 100. Would you agree?
Yeah.
Okay. Now, let's find the force by each positive charge on the negative one. And, we're lucky that both positive charges have the same amount or the same magnitude. So just find it for one of them and then multiply it by 2, right? So, positive and negative, they are this far apart. The positive charge has 1.5. Do you know what the sign means? Micro. Negative charge is negative 6.2 nano. Okay. So we're going to say Fe, or electric force, is equal to K, absolute value, Q1 times Q2 over R squared. You know what the K is, right?
Yeah. 9 times 10 to the power of 9.
Q1 is 1.5 micro. And the Q2 is negative 6.2 nano. r squared is how far they are from each other. Just take the r and square it.
It will be 8 over 100.
Let me know how much you get for the entire number.
Entire number?
So I got 0.104 newtons. That's only for one of them, correct? But let me tell you something. So now for one charge this much. How about for the other charge? You have to add it, right? Okay, so now for the other charge. So that's for one positive charge. And for the other positive charge, the same number. So also 0.104 newtons. And now what? Add them up to each other. So now the final force is 0.104 plus 0.104.
0.208.
But we're not done yet. You know why?
Why?
Because the line here connecting them is not a vertical line or a horizontal line. It's called a diagonal line. Okay, diagonal line. Now, what's the angle here? From here to here? 45. It must actually be given to you in the question. It was not. So we're going to assume it's 45. Okay? Now, we're trying to basically, what's happening here is that you're going to have to draw the horizontal component and the other horizontal component, the vertical component, and the other vertical component. You always do this when your line is diagonal. So, look at the horizontal components. Are they going the same direction or the opposite direction?
Opposite.
So the horizontal components will cancel out. How about the vertical components?
They're going parallel to each other.
Okay, so the vertical ones will add up, correct?
Yeah.
Okay. But it's called a vertical component. That means we have to use the sine part. Because this guy, or the x-axis, is the cosine. So the guy with the y-axis is the sine.
Okay.
Sine of how much? Sine of 45 degrees. So now simply multiply our final answer by the sine of 45 degrees. Let's see how much we get. And I got myself a 0.147, which if you were to round like the book did, would be 0.15 Newton. Good? Here we have two charged objects, and they're both positive. That means that they will repel each other. They will repel each other by exerting an electric force on each other. Okay, that's why the electric forces are heading away from each other. Now, here is our theta, which is the angle. And right now, if I expand this line, this theta is going to have the opposite here, and it's going to have the adjacent here, and it's going to have the hypotenuse here. So, in terms of forces, I have a horizontal force Fe, and my opposite is also horizontal. That means my opposite is also Fe. In terms of the forces, I have the vertical as Fw, and my adjacent is also vertical, so it's going to be also called Fw. And my hypotenuse is going to be Ft, which is the tension force in the string. Now, we're going to say cosine of theta is equal to the adjacent over the hypotenuse, which means Fw over Ft. And the sine of theta is equal to the opposite over the hypotenuse. Opposite being the Fe, and the hypotenuse being the Ft. Now, what I can do is I can find the tangent of theta by dividing sine by cosine, which means I have to divide Fe over Ft by Fw over Ft. So I'm going to have Fe over Ft times Ft over Fw. That means that the Ft will get cancelled. I'll end up with Fe over Fw. That's who? That's going to be the tangent of theta. Fe over Fw. Now if you scroll back to the question, it says that tan theta is equal to sine theta at small angles. We'll be using this to our advantage. Now, let's go ahead and replace Fe with K, Q1, Q2, and these charges are identical to each other. So in the question it's referred to as plus Q. So Q times Q is going to be Q squared over the distance squared, and they are going to be X distance away from each other, over Fw. Fw just means the weight, and the weight is going to be mg. So essentially, my tan theta is equal to, and now it's time to do some math. So I'm going to have kq squared over x squared times mg. That's my tan theta. Now, the question says at small angles, tan theta is equal to sine theta. So now this is my angle. Now I'm going to say that this is the opposite and this is the hypotenuse, but now I'm not going to be referring to forces, and instead I'll be referring to lengths. So the opposite here is the half of x, and the hypotenuse here is the length of the string, L. So now we're going to say that the sine of theta is equal to the opposite over the hypotenuse, so half of x over L. Now it's time to equalize tan theta to sine theta. So I'm going to equalize this guy to this guy. So I'm going to equalize half x over L to k q squared over x squared mg. Now it's time to cross multiply. So we're going to have x cubed is equal to k q squared L over half mg. And if I divide by the half, I'll end up with 2k q squared L over mg. That's for the x cubed. Now it's time to cube root everything. So I'm going to end up with x is equal to the cubic root of 2k q squared L over mg. And that's how we do it. If I have a positive charge here, I'm going to draw a couple of lines coming out of it for electric field. 1, 2, 3, 4, 5. Why would I now draw the line to be shorter? Why does the line become shorter? The line becoming shorter means the field becomes less. So as I move away from the positive charge, the field becomes what? Less, because of this equation. E is going to be inverse with r squared. So more distance from the charge, less electric field. Good? Okay. You see, the electric fields were close to each other. Now they're far from each other. So when they are farther, they're going to be weaker. Agreed? Here we have a charge of plus 3 nanocoulomb placed at the location where the electric field is 400 Newton per coulomb. Find the force. The equation is force is equal to Q times E. Q is the charge, E is the field. Q is 3 nano, and the field is 400. So 1,200 times 10 to the power of -9 Newton. So Q times E is the electric field. Good?
Yeah. That's it.
For this question, yeah. Let's look at this question now. Here we have one positive charge, one negative charge. Distance between them is 6 centimeters, but point P is midway.
Yeah.
That means this R is equal to 3 centimeters, and this R is also equal to 3 centimeters. You want to find the field midway between them. So look, the field will leave the positive charge, and the field will be going into the negative charge. Because both fields go in the same direction, we have to add them up.
Yes. But the voltage will be 0.
Yes, you're right. But the field maximum.
Maximum.
So we're going to do the field by the plus Q with the field by the negative Q because they go in the same direction. So we're going to have K Q over 0.03 squared plus K Q, because absolute value makes it positive Q, over 0.03 squared. Now K is this much. Q is the charge, 4 nano, 0.03 squared. K Q 4 nano over 0.03 squared. You see, because the fields go in the same direction, I add them. If they go in the opposite direction, I do what? I subtract them. Good?
Mm-hmm. So if it's going from negative to positive, you sub here.
1 second. Let me show you when they subtract. Let me show you. So for example, if I had point P here, positive Q, and negative Q, the field will be leaving the positive charge, but going into the negative charge. In this case, they would subtract. In this case, you do the field from here to here. Let's say it's 3 centimeters, random number. And then the field from here to here, which is, let's say, 6 centimeters. The farther the distance, the weaker the field. So the field by the negative Q is going to be less than the field by the positive Q. Why? Because the positive Q is closer. Closer means more field. So the fields will minus in this case. So now you're going to say the field by the plus Q minus the field by the negative Q.
And no absolute value.
Well, there is inside, because electric field is equal to K absolute value Q over R squared.
So always it's going to be positive.
Always. Field will always be positive. Voltage can be negative. It can be. Let's look at this question here. We're given the charge. They want us to find the potential. What equation do we use? V is equal to K Q over R. K is this. Q is this. And R is 2 centimeters, which means 0.02. And you find the voltage. How easy is that?
It's easy. But here it's shagwata.
Look,
Well, the book is scaring you, Mr. Last time I opened the book, I was about to puke.
this is
close. like خلاص يعني this is not طبيعي.
this is the K. So this whole thing here means K. Okay? Let me show you something else. Look, here is a charge. We have lines around the charge. Do you know what those lines are called? They're called equipotential surfaces. So the lines around the charge are potential surfaces. Now, this is the charge that's positive. The voltage right next to it is the highest, and the voltage away from it becomes less. So, if the voltage here is 10, it might become 8 here. It might become 6 here. Now, on any circle, the voltage will not change. So, if it's 10 volts here, it's also 10 volts here. It's also 10 volts here. If it's 8 volts here,
It's 8 volts.
it's 8 volts anywhere on the same circle. Now, there's an equation that you have to know, which is work is equal to Q delta V. Delta V means what? Means the change in the voltage. So, if I take a charge from this point to this point on the same circle,
Yes.
will the voltage change? No. Because 10 to 10 is 0, right? 10 minus 10 is 0. So the work will be 0. The point is, if you take a charge from one point to a different point on the same surface,
Zero.
the work will be
Zero.
0.
What will it take to move a charge Q equal plus from point A to point B?
So, look, to find the work, you gotta apply the equation Q delta V. We're gonna take the charge from point A to point B. So we're gonna do Q VB minus VA. I want you right now to find the voltage at A. I also want you to find the voltage at B. So right now your job is to find the voltage at A by the first charge and also by the second charge, and also find the voltage at B by the first charge and also by the second charge. So what's the equation for the voltage? K times Q1 over R plus K times Q2 over R. And here, K times Q1 over R plus K times Q2 over R. You know what K is, right?
Yes.
How much? 9 times 10 to the power of 9. How much is the Q1?
Q1, it's positive 1 times 10 to the power of negative 2.
And how far is Q1 from point A?
It is 3 centimeters.
No.
Wait, A to Q1?
It's the hypotenuse of 4 and 3. So it's 5 centimeters or simply 0.05. Yes?
Yes.
Plus K is this much. Q2 is negative 6. Wait, Q1 was 4, by the way. 4 nano. Why'd you say?
It's here written Q.
No, I said Q1, man. Okay, how about Q2?
Negative 6.
Nano again. Over. How far is Q2 from point A?
Q2 from point A, it's 3 centimeters. Q2
In meters?
meters or 0.03.
Do the math.
Calculator.
So here it says how much work to move a specific charge from point A to point B. Now we have to find the charge at point A due to Q1 and Q2. We must also find the charge at point B due to Q1 and also Q2. The equation is going to be work is equal to Q delta V. Which Q? This Q. How do you get delta V? By doing VB minus VA. So now your job is to find the voltage at A, and then to find the voltage at B, you have to subtract them. Now to find the voltage at A, what you will do is, you will do K Q1 over how far is Q1 from point A? 5 centimeters or 0.05. Then also K Q2 over how far is Q2 from point A? 3 centimeters or 0.03. Now Q1 is simply this and a Q2 is simply that, with n meaning 10 to the power of negative 9. Now if you do the work, how much will you get? So you got negative 1080, you said?
Yes.
Volt. That's just the voltage at point A. Now, let's find the voltage at point B. We're going to do the same thing, KQ1. How far is Q1 from B?
It is 2 centimeters.
So 0.02.
And then we're going to do the same for Q2.
KQ2.
Divided by
How far is B from Q2?
0.2. I O 2.
You replace the K with how much? 9 times 10 to the power of 9. And Q1 is 4 nano. K again. And the Q2 is negative 6 nano. Go ahead, let me know how much you get. Which equals to negative 900 volts. Now you're going to do delta V is equal to Q. You're going to do work is equal to Q delta V. So Q VB minus VA. Q is already given to you in the question, which is 1 times 10 to the power of negative 2. And VB is negative 900 minus VA, which is negative 1080. So this much, negative 900 plus 1080. So this much times 180, and we'll get 1.8 joule. Any questions?
Nope.
We have two charges placed in an area, and they will cause a third charge to move away because of electric repulsion. Okay. Now, for example, let's say that here we have a negative charge getting repelled by other negative charges. One here and one here. It gets repelled. So if it gets repelled, it will now acquire a kinetic energy.
Yeah.
But the first law of thermodynamics says no energy is created nor destroyed, meaning the newly acquired kinetic energy of this negative charge came at the expense of the
Repulsion?
potential energy of the system.
Like what? How potential?
So the Ke of this negative charge increased because the potential energy, the potential electrical energy of the system decreased. Okay? So if Ke goes up,
to get repulsed, the kinetic energy rises.
well, the charge was not moving, but now it starts to move.
Yes.
That's called speed, which means kinetic energy. Good. Okay. Now, the strength of the electric field depends only on the length of the electric field line. Not how many field lines we have there, just the length. Good? So here, the electric field line around charge R and charge S and charge T. Do they have the same length as each other? They do. look,
How?
this line and this line, and let's say this line and this line, they have the same length as the lines that are right next to us. Let's say 1, 2,
This.
3, and 4. And the same exact length of the lines around T. 1, 2, 3, and 4. Okay? So basically, R, S, and T, they have the same electric field as each other. And so E of R is equal E of S is equal E of T. Good. How do I know? Because the length of the lines around them is all the same. But there's one issue here. How come the lines from S are much farther than lines from R or the lines from T? How would the lines from S be much farther? Would you know? It's because the charges are different. So now, let's see what I can write. I can write that the electric field of R is same as the electric field of S, same as electric field of T. So K, QR over. Now, how far is this point from the next line? How far is it? 1, 2, 3, right? So this R is 3 units farther from the lines. We're going to put 3 squared because the equation of E is KQ over R squared.
Here as well it's 3. So T equals to R, right?
Smart. So we're going to say here K QT over R squared, 3 squared.
Yeah.
But how about the distance of S to the next line? 1, 2, 3, 4, 5, 6. So K
Double almost.
QS over 6 squared. Now, 3 squared is
9.
6 squared,
36.
3 squared, 9.
9.
Now, what I want from this relationship, I want to find the ratio of QR to QS. Let's cancel the K's.
Also the Q's, right?
No, they have different Q's, so I cannot. So I'm going to say QR over 9 is equal to QS over 36.
QR over QS equals to 9. So that's the answer?
I want the ratio. So I'm going to say that Q R over QS is equal to 9 over 36. If you were to divide 9 by 36, what would you get? 1 over 4.
Yeah.
So now I know that QR is equal to, QS is equal to 4 times QR.
Same goes for QS and QT.
Exactly. So QS is equal to 4 times QT. So essentially what this means that when the space around the charge is larger, it's because the charge is larger itself. Larger space means larger charge. Okay. Do you know what this straight line here means between two charges? It means that we have a zero voltage. How could you have a zero voltage between two lines?
They are different charge, right?
They are opposite in sign, exactly. One is positive and one is negative. So therefore, when I look at figure 1 right now, do I see this straight line?
They are opposite sign.
No, بالعكس.
It should be negative and positive because they are interacting.
My friend, If I get 0 voltage, it's because I have a plus charge and then minus charge. If I don't have a 0 voltage, they are the same sign.
Repulse.
So the straight line means 0 voltage. The straight line means the charges have the opposite sign as each other. Okay?
Okay.
Now a question. In figure 1, why do you think that the sphere around the charge on the left is bigger than the sphere around the charge on the right? Why do you think so?
Because it is bigger inside.
Thank you. So the magnitude of this charge is more. Okay?
Yeah.
Now, what we see here is a capacitor, which essentially means two parallel plates that can store charge. And here what we have is a battery connected to the capacitor. The positive plate of the battery makes this plate positive, and negative plate of the battery makes this part negative.
Yeah.
So essentially charge gets stored on the capacitor.
This means that this side is what and this side was what?
The smaller side of the battery is negative,
Negative.
and the bigger side is
Positive.
positive. Now, if you were to insert a dielectric between the two plates of the capacitor, what you will do is you will increase the capacitor's ability to hold on to charge. So the capacitance will increase. Now, this dielectric material is counted in numbers. For example, we might say dielectric of 2. That means the capacitance will increase by a factor of 2. I might say dielectric of 4. Capacitance goes up by a factor of 4. Whatever dielectric is, which will always be more than 1, capacitance will go up by the same amount. Now, in our scenario, we have dielectric of 2, capacitance will go up by a factor of 2. Now, we are inserting a dielectric in the capacitor, the capacitance will increase. Now, because your battery is still connected, that means that the voltage is constant. The voltage is what? Constant. But the battery will always provide a source of charge to the capacitor that's variable. That means that the charge is variable.
So what does that mean?
Look, there's a new equation you have to know. Q is equal to C times V. The voltage is constant, meaning that Q is going to be direct with C. And so if the capacitance increases by a factor of 2, what's going to happen to the Q?
Increase by a factor of 2.
Because they're going to be directly proportional with each other. Good? So the Q will go up by a factor of 2. What's going to happen to the electric field? I want you to know this equation. It's provided in your equation sheet. This equation shows you what's the relationship between E and Q. Direct or inverse?
It's direct.
Direct. So if the Q goes up by a factor of 2, the E will also go up by a factor of 2.
Okay, but what's this rubbish down here?
Rubbish?
Like 3OA, it's very...
No. It's called epsilon naught.
Epsilon,
It's a constant, 8.85 times 10 to the power of negative 12.
And what about the A? A,
A is the area of the capacitor.
so it's 10 to the power of negative 2. No?
A is the area, which is not given in the question. Now, even though the E is direct with Q, at the same time it's going to be inverse with kappa. Kappa is something called dielectric constant, which is this one here. And so since the kappa increased by a factor of 2, E will also decrease by a factor of 2. Correct?
Yeah.
So here it says E will increase by a factor of 2. There it says E will go down by a factor of 2. So what's going to happen to E? Remain the same. Remain the same. Because essentially E is going to be direct with Q, inverse with kappa. Q is 2, kappa is 2. So essentially, no change.
Yeah.
Good. Now, let's take the same scenario as before. A battery that has been connected to a capacitor. Let's now put a dielectric inside the capacitor. A dielectric has one importance to make the capacitance more. If dielectric is 2, the capacitance will go up by a factor of 2. We agree on this one?
Yes.
Good. Now, let's now disconnect the battery. So imagine the drawing to be the following. Capacitor without any battery. If there is no battery, there is no more source of charge.
Yes.
Which means that now the charge is constant, but now the voltage is going to be variable.
And if the Q is constant, is C gonna be constant as well? No?
Ouch. You hurt me. Q is constant, meaning that C and V will now be inverse with each other. So now if C goes up by a factor of 2, V will go down by a factor of 2. How about our friend E? As you already know, E is going to be direct with Q, inverse with kappa. Q was the same, wasn't it? Put 1. Kappa was 2, wasn't it? When E is inverse with 2, that means that E will decrease by a factor of 2.
So it'll be -2.
Not -2. But let's say it was 1000, now it's going to become 500.
Yeah, 5. Decrease, يعني how? Divided by 2?
Divided by 2.
Uh-huh.
Divide by 2.
Subtract.
Decrease by a factor of 2 means divide by 2. Increase by a factor of 2 means multiply by 2. Let's talk about the electric potential energy in a capacitor. It has an equation. U is equal to half CV squared. U is equal to what? Half CV squared.
Yeah.
Let me ask you a question. If the C goes up by a factor of 2 and the V is constant, what's going to happen to the potential energy?
Wait, so if C is up by 2, V should go down by 2.
Wait.
But if
When was the case when the V was constant? When the battery
is there.
is connected. Exactly, is there. So now, if C goes up by a factor of 2 and V is constant, what happens to the electrical potential energy? It will go up by a factor of 2. Yes, because essentially this energy is direct with the capacitance. Now, let's disconnect the battery. So now we're going to say UC is equal to half CV squared. If we disconnect the battery, what was constant? The Q, right?
Yes.
The Q is constant. When the Q is constant and the C went up by a factor of 2, the V went down by a factor of 2. Do you recall?
Yeah.
Okay. Now, UC is going to be direct with capital C and V squared, correct? Instead of C, put 2. How about the V? Because V goes down by a factor of 2, instead of the V, put half. So half squared. Now, what's 2 times quarter? Half.
Yeah.
That means that the UC will go down by a factor of 2. Would you agree?
Yeah.
Very good. All right, let me give you a new equation. Capacitance is equal to epsilon kappa area over distance between the capacitor plates. So we have a capacitor whose two plates are parallel, whose capacitance is 10 nanofarad.
Nanofarad yani şu.
Nano means 10 to the power of negative 9. What's in your equation sheet? The charge is 15 micro. Micro means 10 to the power of negative 6 coulomb. What's the potential difference between the plates? Which basically means they're looking for V. So you're going to say Q is equal to CV. So V is equal to Q over C. Q is 50 times 10 to the power of negative 6. C is the capacitance, 10 nano. So 10 times 10 to the power of negative 9. Do the math and let me know how much you get. Exactly, 5,000 volts. That was part A. Let's now do part B. Now they're saying in part B, if the plates were separated by a distance of 0.2 millimeter, find the area. So distance is 0.2 millimeter, which means times 10 to the power of negative 3. Find the area. So we're going to say C is equal to epsilon kappa A over D. You know how much is the capacitance, right? It's given in the question as 10 times 10 to the power of negative 9. How much is the epsilon again? It's constant?
Yeah.
8.85.
8.85 times 10 to the power of 12.
Negative 12. Okay? Now, for the kappa, did the question mention it in the question itself? Did they mention how much is the kappa?
Kappa.
No.
Oh.
So you're going to have to assume it's a 1.
What? Allah. You have to assume, you have to guess. What's this physics?
Keep the area the same. And distance is this. Now what do? You cross multiply. So this times this is equal to kappa A. And now find A. Find the area, right? Just simple substitution that will barely come in the AP. For this question, what do you think we should do? What equation do I use? What am I given? I'm given charge to be this, correct?
Yes.
I'm given distance of 2 millimeter. I'm given capacitance of 1 micro. Find electric field. What equation do I use? Look, I know that Q is equal to CV, correct?
Yes.
You should also know another equation. V is equal to ED. We're looking for E. So E is equal to V over D. But
E isn't given.
let's find V first. Q is given, right?
Yeah. C is given.
C is given.
D is given. But if we want to find V, we need to know E. But E is not given.
No, we have Q, we have C, we can find V.
Yeah.
So V is going to be 4 volt.
Wait, so if why 4 volt? Like if you divide, you're gonna get a 4 volt?
Yeah.
Yeah.
So it's going to be 4 over distance of 2 times 10 to the power of negative 3. We will get 2000 Newton over Coulomb.
Wait, what did you do in this part, mister?
I just divided V by D.
Yeah.
We'll get 2000.
So that's the question.
Hmm?
So that's the question?
Yeah. So the equation for work when discussing electric charges is equal to Q times E times D times cosine of theta.
Oh, I need to refresh myself. Like small refresh for 1 minute or 2 minutes. Because I'm studying.
You want refreshments?
Like 1 minute or 2 minutes.
You want refreshments? We have refreshments in the fridge if that's what you're...
I'm studying wavelength.
Yeah, I don't know. They're going backwards. They're studying from...
Last chapters.
Yeah, I don't know. They always do that for some reason in physics. Anyways, man. Yeah, it's weird. But look, no one here knows this equation. It's the first time they see it, I think. So you're fine. QED times cosine of theta. Now, when I have two plates with opposite charges, the electric field will be going from the positive charge to the or positive plate to a negative plate, basically. Now, if I were to put a proton here, in which direction will it go?
To the right, to the right.
So it's going to go in the same direction as the electric field, correct?
Yes.
Okay. So what's going to be the cosine of theta in that case? The cosine of how much? Cosine of 0, exactly.
Oh, why 0?
Because they're parallel to each other. The proton's direction of movement and the electric field are parallel to each other, which makes the cosine equal to 1. Okay? The angle's 0. So now for a proton, we say that W electric is equal to QED times 1, which is just QED.
Yes.
Now, how about a an electron?
So wait, D is distance, E is energy?
D is distance
Yeah.
between the two plates.
Yeah.
E is the electric field.
And Q is charge. Okay.
Thank you. Now, we did this for a proton. Let's now do it for an electron. So now, if I were to place an electron here, in which direction is it going to move? Right or left? Left. So it's going to be going in the opposite direction of the electric field, correct?
Yes.
Okay. Now, so what's going to be my theta then?
Is it still 0?
The theta.
Yeah, because like it's
No, this and this are called anti-parallel. So the angle has to be 180.
I've never.
Because look, if one arrow is going this way, one arrow is going this way, they're far away by half a circle. 180. Now the cosine of 180 is equal to a negative 1. Now let's go back to our equation. So work electric is equal to QED cosine theta, correct?
Yes.
Now, electron is a positive Q or a negative Q?
Negative Q.
Negative Q. So now instead of Q, I'll put negative Q.
It's going to be negative ones. It's just
Times E times D times cosine of 180. And what's the cosine of 180? Negative 1 as well. So negative Q times E times D times negative 1. The whole thing comes out to QED. Correct?
yes.
Okay, we get that part.
Yes.
All right, good. Let's move on to the change in electric energy. The change in electric potential energy. It will be having the negative sign of work. Negative of work. So negative QED cosine of theta. Good? Okay. Now, how about the equation to find the kinetic energy final? That would be the kinetic energy initial minus change in delta U electric. Okay. So, KF means the final kinetic energy. and Ki means the initial kinetic energy, which will be 0 for most of the cases if they say the object started from rest. Okay.
So KF just equals work. So time.
You are absolutely correct about that. Very good. Okay, with that in mind, we can go to a question. Let's do this question here. So the question says that we have a nucleus of uranium, which contains 92 protons, absorbs an additional neutron, and as such, it will now break down in a process called nuclear fission. It will now break down into two smaller nuclei, okay, which is two palladium nuclei. Each one has 46 protons, and each one has a radius of 5.9 multiplied by 10 to the power of negative 15 meters. They will then fly away from each other because they will repel each other, and they were initially at rest, and at some point they're going to be very far apart. Find the kinetic energy of the system. Okay, let's start. So look, first of all, let's just imagine those two palladium nuclei. So we're going to draw one circle. We're going to copy paste it into a circle that's going to be placed right next to it. Like this. Now, how much is the radius of a single nucleus? And the same goes for the other nucleus. So now the question is, how far are the centers of the nuclei from each other? 2 times that, right? So now the distance between the centers of the nuclei is equal to 2 times 5.9 times 10 to the power of negative 15 meters. This is called the R in the equation.
Should the distance between them is like full circle?
The distance has to be a full circle, yes, because it's distance between the two centers, not the edges, not the outsides. Now, how much is the charge of the nucleus on the left? How much is Q1? It's equal to 46 protons. Okay?
Yeah.
And how much is the charge of the nucleus on the right?
So do we not take electrons into consideration?
No. No, we don't. Because they only focused on the protons. And they also flew away. That means they were repelled.
If you're both positive?
Yes. And by the way, even if you took both as negative, you get the same answer because the minuses will cancel. So you're fine. Now, what's the equation? We're going to say Kf is equal to Ki minus delta UE. Now, did they say that they were at rest at some point?
Yes.
Which basically means that the Ki has to be as 0 minus delta U. Now, what's delta U? U final minus U initial. Now, guys, look, they were initially at rest. At some point, they became very far apart. Correct? Okay. What's the equation for U? Do you guys know? It's equal to K, Q1, Q2 over R, not squared. So I'm going to say that Kf is equal to minus UF plus UI. Let's start to replace. So minus K, Q1.
Hold on, I'm confused here. Why did we negate? Oh, okay.
Okay. So Kf is equal to minus K, Q1, Q2 over R final plus K, Q1, Q2 over R initial. Now, they said that at some point, in the end, they became very far apart. And very far apart in physics means that you have to replace the distance with infinity. Take a moment to observe that.
So how do you divide it by infinity?
0. Anything divided by infinity is 0. So we're going to get here 0 plus. And now it's time to replace. So this is going to be on you, the replacing part.
So
Am I asking for too much? Okay. 9 times 10 to the power of 9. What's Q1? 46 protons. That means 46.
Q1
The initial field, the one that's like 92, I don't know how much.
No. We're talking about the two palladium nuclei, each one having 46 protons.
Okay, so 46.
Times elementary charge, right?
So how? Should be also 46.
Yeah, so 46 times this. They're both 46 protons, right?
What is this?
This is the Q1, 46 protons.
6 times 10 to the negative, I don't know how much.
Yeah, this is called elementary charge. It's found in your reference sheet that you guys have to know. Over the R initial, and they were basically 2 times 5.9 times 10 to the power of negative 15.
Yeah.
And now you guys can do the work and you can find the KF. And that's it. You don't have to, I did the whole work, but basically for next time you guys will try something. Okay, good? Let's do another one. Alright guys, so here we have an electron given this charge and given this mass released from rest in an electric field. So there's an electric field, positive plate, negative plate. The field is going to go from left to right, and the electron is going to be going spot negative. It's going to be going in where direction? Which direction?
To the left.
To the left, thank you. So now they're saying find the speed of the electron. Now look, you're going to say Kf is equal Ki, which is 0, minus delta UE. So Kf is equal to minus, and what's delta UE?
You
U final minus U initial.
Minus U initial, exactly. Okay. Now, I don't have the initial distance, right? I just know that it moved by 0.300 meters. Okay? So, when this happens, when you only have one distance, what you do is you just say that U is equal to negative work, which basically means negative QED cosine theta. That's what you do. Okay? Now, so K final is equal to the negative of U, basically. Or K final is equal to the negative of negative QED cosine of theta. Okay? No.
For which should be negative anyway.
Sorry?
The final answer will be negative.
You can't have a negative KF. It has to be always positive.
Then how?
How? Okay, well, let's cancel the minuses, and you will get QED cosine theta. Correct?
Yeah, cosine theta is negative 1.
But the Q is also negative. So now KF is equal to Q is negative 1.6 times 10 to the power of negative 19. Now, E is the electric field, which the question says is basically 200. The D is the 0.300. And cosine of 180, which is negative 1. So your answer comes out to a positive. Correct? Okay. Do you have something? No. So let's go ahead and do that. Let's see how much that is in the calculator. You guys can. Yep, 9.60 times 10 to the power of negative 18, I think, joules. Is that what you guys got? Good. But the question doesn't want us to find the KF. The question wants us to find the speed.
No, the calculator.
So once you have found the KF, how can you find the speed?
From the calculator, it's wrong.
So my calculator is wrong. What is this?
Your calculator is wrong?
Change
What do you mean?
change it.
So look, the equation to find the velocity from the KF would be half mv squared. Which, by the way, is in your equation sheet.
Kinetic energy.
Yeah, I don't know how you guys are.
Yeah, so we're
Yeah, whatever, man.
close-minded. Whatever.
I didn't go that far. Half times The mass of the electron, at least find me the mass of the electron correctly.
It's given.
times
Sir,
10 to
it's
the power
given.
of
The
negative
mass is
31.
given. 911.
Don't be lazy. Okay, now.
Mister,
We need
is the mass given?
Yeah, it is, but it's not always given in the exam. Now it's your job to find the v squared and then square root.
Square root.
Look, first of all, whatever is next to v, which is this, goes to the bottom,
Yeah, we know. Well, no, it is.
and not everyone knows. And now it's square root both sides to find the v. So please go ahead and please get it right.
What if mass is not given?
You find from the reference sheet. God gave you eyes and hands. No, I'm just saying what God gave you. Where's the insult part?
So I'm not saying, I'm telling him. Yes, I can go.
Just don't insult him next time.
5459008.
4.59?
4550832.271.
I'm sorry. So you said we have 4, 5, 9,
You know how to use calculator?
9,
4.5 times 10 to the power of negative 6, that's it.
4.59 times 10 to the power of?
Negative 5.
No, it's actually 6, but okay.
-5? 2 times
If, if you are going to hide numbers on the right of the point, the power has to be positive, not negative.
Like that, positive, and then going back like that, it's negative.
Probably, yeah. But also, electrons are going to be very fast. So they must always have a speed in the millions or like the hundreds of thousands, you know? So, great job.
3, 4, 5.
We did it.
Great job, guys. You guys are good listeners. You let me do the work. Okay, now, let's give you, okay. Now, if I ask for the electric potential energy of a system of charges, what equation do you like to use? Or what equation do you have to use if I have a number of charges? Look, if the question says, find the electric potential energy of a 3-charge system, that's the equation to use.
So the same equation but times 3.
Whatever you think, man. Now let's show you a question. Let's see if you guys can demonstrate that intelligence. All right. Here's the question. They gave us 3 charges. Now, first of all, you guys have to draw them to see how they're far from each other. For example, I'll draw you the first one. The first charge is at the origin, right? It's Q1.
Yeah, maybe they are far, like 4 centimeters.
No, they're saying x0 and y0. That means origin. The second charge is at x0 and 4.
I might hear you.
So that's the Q2. It's 4 centimeters away from the Q1. And
It's
the
the right triangle.
yes, and the Q3 is at 3 and 0. So it's here.
So now I have to do some calculation here.
Yeah.
Now, they're saying find the total potential energy of these point charges. So what you do is you will say, okay, we will do K, Q1, Q2 over how far they are from each other, plus K, Q1, Q3 over how far they are from each other, plus K, Q2, Q3 over how far, and of course you must always convert the centimeters to meters. So guys, please go ahead, put the correct numbers, give me the final correct answer, then we can believe in you. Go ahead.
So the first one.
So the Q1 and the Q2 are 0.04 from each other, Q1 and Q3 are 0.03, Q2 and Q3
0.0.
are,
0.05.
Square root of.
thank you.
So you know the patterns in Pythagorean theorem?
Yeah.
3, 4, 5, 7, 8, 12, something like that.
6, 8, 10, yep.
6, 8, 10.
Now, it's time for you to replace, that's the Q1. Don't forget to convert nano, right? That's the Q2, it's negative, and that's the Q3, it's positive. So go ahead and work on it. And start to replace in the Q's. So this is the K. This is the Q1.
So now it's 10 to the power negative 9, right?
Yep. And this is the Q2.
And you guys keep replacing.
So
Rest.
why did you get these numbers? Is it something like that?
So the final answer is going to be negative 1.18 times 10 to the power of negative 5 joules. Okay, so look, here we have a capacitor, which means two parallel plates holding a charge. Now the capacitance is equal to 10 nanofarad. Farad is the unit of capacitance and nano means 10 to the power of negative 9. The charge on the capacitor is equal to 50 microcoulomb.
That's 10 to the power negative 6.
50 times 10 to the power of negative 6, exactly. A says, find the potential difference. Now, please look for the equation sheet for the correct equation to use. If you have C and a Q, to find V. So Q is equal to C times V. So V is equal to Q over C.
Isn't it U over Q? What?
There is no U in there.
Oh wait, oh my, I'm missing.
So this is the Q. And this is the C. And we get the answer to be 5,000 volts.
No, it's asking for the area.
That was part A. Part B says if the separation between the two capacitor plates is equal to 0.2 millimeters, find the area on each plate. So we're going to say capacitance is equal to epsilon kappa area over distance. We're looking for the area. So that means that area is equal to whatever is next to it goes in the bottom. Whatever is not next to it goes on top. Now it's time for you guys to replace. Now, did they give us the dielectric constant in the question? No, that means you assume that kappa is equal to a 1. Epsilon is going to be 8.85.
That's the power of negative 4.
Constant? Okay.
Capacitance we already have given earlier as 10 times 10 to the power of negative 9. And D is going to be 0.2 divided by 1,000.
It's gonna be 0.225.
So what's the answer in the end? 0.23 meters squared if you were to round, correct?
You said don't round.
That wasn't me. Okay,
Didn't you see that?
good. Now we have a new question. I gave you the charge, the Q. I gave you the distance between the two plates. I gave you the capacitance. All I want is the amount of the electric field. I want the E.
Only. No?
Look guys, you will say V is equal to E times D. But we don't have V, so you must find it by using Q is equal CV. This is going to be the first equation. That's going to be the second equation. This is in the equation sheet. That's also in the equation sheet.
Where?
Sir, can you just...
So the charge is this. The C is 1 micro. So the V is going to be, is it? Now, V is for, we're looking for the E. D is 2 millimeter. So E is equal to 2,000 Newton per coulomb.
So do you think our part is less than the end of the